Lesson: Machine learning techniques for threat attribution. Machine learning has become a cornerstone in the domain of cybersecurity, particularly in the field of threat attribution. This area focuses on identifying the responsible parties behind cyber threats, a task of growing complexity due to the increasing sophistication of attacks and the anonymity afforded by the Internet. Machine learning techniques provide powerful tools for extracting actionable insights from vast amounts of data, enabling cybersecurity professionals to trace the origins of attacks more effectively. One of the foundational approaches in machine learning for threat attribution is the use of supervised learning algorithms. These algorithms require a labeled dataset to train the model, wherein the inputs are the features of the cyber incidents and the outputs are the labels indicating the source or type of attack. For instance, decision trees and support vector machines are commonly used supervised learning techniques that can classify attacks based on their characteristics. A practical example involves using decision trees to identify the likely origin of a DDoS attack by analyzing patterns in network traffic data, such as packet size and frequency. This approach allows security teams to rapidly pinpoint whether an attack is likely coming from a botnet or a specific threat actor group, thereby streamlining the response process. Unsupervised learning techniques, such as clustering algorithms, also play a critical role in threat attribution. These algorithms do not require labeled data and are particularly useful in identifying new or unknown threats. Clustering algorithms like k-means or hierarchical clustering can group similar incidents together based on their attributes, highlighting patterns that might indicate a common source. For example, by clustering network logs, analysts can uncover previously undetected attack vectors that share similar attributes, such as IP addresses or malware signatures. This can guide further investigation and help in attributing these clusters to specific threat actors. Another advanced technique in this domain is the use of deep learning models, particularly those based on neural networks. These models are highly effective in processing unstructured data, such as text and images, which are often encountered in cyber threat intelligence. Convolutional neural networks can be used to analyze network traffic data visually, transforming the data into images and identifying anomalies or patterns indicative of specific threat actors. Similarly, recurrent neural networks are suitable for analyzing sequences of events, such as login attempts or command sequences, enabling the detection of malicious behavior patterns that can be traced back to particular adversaries. Incorporating machine learning into threat attribution processes also involves the use of practical tools and frameworks that facilitate data analysis and model deployment. Tools such as TensorFlow and PyTorch provide robust libraries for building and training machine learning models. TensorFlow, for instance, allows for the rapid prototyping of deep learning models, which can be used to analyze complex datasets for threat attribution. By leveraging TensorFlow's capabilities, cybersecurity professionals can develop models that process large volumes of data in real time, enabling quicker identification and attribution of threats. The practical application of these techniques is exemplified in several case studies. One notable example is the use of machine learning in identifying the perpetrators of the WannaCry ransomware attack in 2017. By analyzing the ransom notes and the propagation methods used, machine learning models were able to link the attack to the Lazarus Group, a known threat actor associated with North Korea. This attribution was possible due to the distinctive linguistic patterns and coding styles identified in the malware, which were compared against a database of known threat actor profiles. Despite the efficacy of machine learning in threat attribution, there are challenges that practitioners must navigate. One significant challenge is the quality of the training data, as inaccurate or biased data can lead to incorrect attributions. Ensuring data integrity and diversity is crucial for building reliable models. Additionally, adversarial machine learning poses a threat, where attackers may attempt to deceive models by introducing subtle perturbations to the data. Techniques such as adversarial training, where models are trained on both clean and adversarial examples, can mitigate these risks, enhancing the robustness of machine learning models in threat attribution. Another consideration is the interpretability of machine learning models. Deep learning models, while powerful, often function as black boxes, making it difficult to understand the rationale behind their predictions. Explainable AI frameworks are being developed to address this issue, providing transparency in model decision-making processes. For example, the local interpretable model agnostic explanations technique can be used to interpret the predictions of a neural network by analyzing the contribution of each feature to the final decision. This insight is crucial for cybersecurity professionals who need to justify their findings to stakeholders or legal entities. To enhance proficiency in applying machine learning to threat attribution, cybersecurity professionals should engage in continuous learning and adaptation. This involves staying updated with the latest research and advancements in machine learning and cybersecurity, as well as participating in communities and forums that focus on threat intelligence and cyber threat hunting. Collaboration with interdisciplinary teams, including data scientists, network engineers, and threat analysts, can also foster a more holistic approach to threat attribution, leveraging diverse expertise and perspectives. In conclusion, machine learning offers transformative capabilities for threat attribution, enabling more accurate and efficient identification of threat actors. Through supervised and unsupervised learning techniques, deep learning models, and practical tools like TensorFlow, cybersecurity professionals can enhance their threat intelligence efforts. However, challenges such as data quality, adversarial attacks, and model interpretability must be addressed to fully realize the potential of these technologies. By continually refining their skills and leveraging advanced frameworks, professionals can effectively utilize machine learning to safeguard against cyber threats and contribute to a more secure digital landscape.